Hello there. In this video we're going to talk about an application of integrals, namely to economics. So let's just review just a couple ideas that are presented in a basic economics course. So let's assume the quantity of goods is listed on the horizontal axis and the price of those goods is listed on the vertical axis. Let us consider we have two curves in space. Let us call this curve PS of Q, which is going to correspond to the supply curve. And let us also consider another curve in space known as the demand curve. We're not going to get into the interpretation and the detailed applications of these. We're just going to sort of show how we can solve some of the problems in economics with integral calculus. So as we may already know, the place where the supply curve and the demand curve intersect is typically referred to as the equilibrium point. So I'm going to notate the horizontal component of the equilibrium as Q star, and I will refer to the vertical component of the equilibrium point as P star. So in this video, we're going to be talking primarily from the consumer perspective in terms of how you can use integrals to solve problems. So we're going to begin by defining a couple terms that we're going to be calculating. The first term I'm going to abbreviate simply by CW, and this is going to correspond to the willingness to spend for a consumer. And this is defined to be equal to the integral from 0 to Q star of the demand curve with respect to the quantity. So if we look at our distributions, so this is Q and this is P, and our demand curve is the decreasing term. So the integral from 0 to Q star, let's assume that our equilibrium point is here. Then CW, the willingness to spend, is going to be this region here. So this is going to be CW. So in terms of the business side of things, we want CW to be as high as possible. So let us now define CE. CE is the consumer expenditure, which is defined to be equal to the integral from 0 to Q star of P star dQ. So same picture. Let's draw our demand curve. So this is going to be Q, this is going to be P, and this is going to be the demand curve with respect to Q. So if Q star is here, that means P star is going to be up here. So the area underneath P star from 0 to Q star is going to be this region here. So this is going to correspond to C. And the consumer expenditure typically refers to, I'm not going to really get into the macroeconomic details of it, but it's related to the ability to acquire goods or services from a particular industry or service. And from here we can define what CS is. So CS is the consumer surplus, which is defined to be equal to the willingness to spend minus the consumer expenditure, which from the integral definition is going to be the integral from 0 to Q star of the demand curve with respect to Q minus P star dQ. So if we look at our distribution, so Q, P, P dQ, Q star, P star, so CS is going to be this region. My curve changed colors. So this is going to be my CS, my consumer surplus. And just as a side note, there are similar concepts and definitions. For the business side, so the business perspective mainly focuses on the supply curve instead of the demand curve and the interaction between business and consumer. So let's look at a numerical example of how to calculate these three quantities, namely the willingness to spend of a consumer, the consumer expenditure, and the consumer surplus. So let us assume, suppose that the demand curve is equal to Q plus 2 divided by Q plus 1, and the supply curve is equal to 0.3 Q. And I'm not going to get into the details of how to generate these functions, but let's assume that those are what they are. Now, as always, if you have a function whose degree of the top is equal to the degree of the denominator in terms of rational expression, you may want to perform long division to make this a little bit easier. So if we divide Q plus 1 into Q plus 2, we know that Q times 1 is going to be Q. Then we have Q plus 1, then we subtract. So Q minus Q is 0 and 2 minus 1 is 1, so this is the remainder. So if that's the case, we can rewrite our demand curve to be equal to the quotient 1 plus the remainder over the divisor Q plus 1. So this is typically a lot easier to deal with. So there's our demand curve and our supply curve. Let's rewrite that again, 0.3 Q. So the first thing we're going to do is locate our equilibrium point, our market equilibrium point. So this occurs when the demand is equal to the supply, which is going to exist when 1 plus 1 over Q plus 1 is equal to 0.3 times Q. So let's solve this equation for Q. So I'm going to multiply both sides of this equation by Q plus 1. So I'm going to have Q plus 1 is equal to 0.3 Q times Q plus 1. So that's going to give me Q plus 2 is equal to 0.3 Q squared plus 0.3 Q. So now I'm going to isolate. I'm going to move my Q term over here. So I'm going to subtract Q from both sides. And I'm also going to subtract this 2 from both sides. And those are going to cancel. So that's going to give me 0.3 Q squared minus 0.7 Q minus 2 is equal to 0. I typically don't like working with decimals, so I'm going to multiply both sides of this equation by 10. And that's going to give me the quadratic equation, 3Q squared minus 7Q minus 20 is equal to 0. Now you can easily factor this expression using whatever methods you're familiar with. So we can rewrite this as 3Q plus 5 times Q minus 4 is equal to 0. We know that you can't have negative quantities in a traditional system, so by this restriction we only have one 0 that we're interested in, and that, namely that one. So we have Q is equal to 4. So this is going to be my equilibrium quantity. So since Q star is equal to 4, P star is going to be the value that you obtain by substituting the quantity equilibrium in either the demand or supply curve. It doesn't really matter. So I'm going to evaluate the supply curve at Q star. So that's going to be 0.3 times Q star, which is 0.3 times 4, and you can find that to be 1.2. So that means Q star is equal to 4, and P star is equal to 1.2. So that's our equilibrium pair. So now let's calculate our willingness to spend, our consumer expenditure, and our consumer surplus. So our willingness to spend is going to be equal to, by definition, the integral from 0 to Q star of the demand curve with respect to Q. So that's going to be equal to the integral from 0 to 4 of 1 plus 1 over q plus 1 dq. By the fundamental theorem of calculus, we know that this is going to be equal to q plus the natural log of q plus 1, evaluated as q goes to 4 and as q goes to 0. So when we plug in 0, we get 0 plus the natural log of 0 plus 1, which is 0 as well. So this has no value contribution to our integral. So this is going to be equal to only 4 plus the natural log of 4 plus 1, which is 5. And you can find that this is going to be approximately equal to 5.61. And again, I'm not going to get into the interpretation of what does it mean for CW to be 5.61, but just think about it, if you're a business, you want CW to be as high as possible. With respect to what, that sort of depends on the situation. So similarly, the consumer expenditure, by definition, is the integral from 0 to q star of p star with respect to q. So p star we've already found to be 1.2. So this is the integral from 0 to 4 of 1.2 with respect to q, which is just going to be 1.2 times q evaluated from q goes to 4 to q goes to 0. Again, q goes to 0 does not contribute anything. So this is going to be equal to 1.2 times 4, or just simply 4.8. So, and finally, my consumer surplus, which by definition is going to be my willingness to spend minus my consumer expenditure, which is going to be approximately equal to 5.61 minus 4.8. And we can find that that is equal to 0.81. And again, I leave the interpretation for the reader, but again, this is some basic applications that you can use integration for in terms of economics.